Hey guys, and welcome to another fun and easy machine learning tutorial on artificial neural networks. Deep learning and neural networks are probably one of the hottest topics right now. Large corporations and young startups alike are all gold rushing into the state-of-the-art field. If you think big data is important, then you should care about deep learning. Deep learning and neural networks is currently driving some of the most ingenious inventions of the century. Their incredible ability to learn from data and the environment makes them the first choice for machine learning scientists. Please subscribe and click that bell icon to join our notification squad. Deep learning and neural networks lies in the heart of products such as self-driving cars, image recognition, recommender systems, and the list goes on. Evidently, being a powerful algorithm, it is adaptive to various data types as well. People think that neural networks is an extremely difficult topic to learn. Therefore, either some of them don't use it, or the ones that do use it as a black box. Is there any point in doing something without knowing how it's done? No. That is why you've come to the right place at Arduino Startups to learn about artificial neural networks, so sit back, relax, and let's see how deep the rabbit hole goes. What are neural networks? Neural networks, also referred to as artificial neural networks, is a name given to its artificial representation of the working of a human being's nervous system. I'm sure by now you've seen this diagram of a neuron. A neuron is comprised of the following major components, which are dendrites, which take its input from other neurons in the form of electrical impulses. The cell body generates inferences from those inputs and decides what action to take. And then you have the axon terminals, where they transmit outputs in the form of electrical impulses. In simple terms, each neuron takes input from numerous other neurons through dendrites. It performs the required processing on the inputs and sends other electrical impulses through the axons into the terminal nodes, from where it is transmitted to numerous other neurons. Artificial neuron, the heart of a neural network. The neuron of a neural network is an activation node. Here is where all the action happens. The activation node takes the input from the predecessor nodes, applies the learning parameters to generate the weighted sum, and then passes that sum to an activation function that computes the composite prediction or probabilities. This is known as a perceptron, which can be understood as anything that takes multiple inputs and produces one output. This generation of fused predictions is what happens at every node in a neural network, and because of this, the predictions are progressively processed until the final output is generated. So looking a bit at this image, we have inputs, which can be either from our independent variables or from other neurons. These inputs are multiplied by weights. The weights are assigned to the synapses and denoted as W. They decide what's important and what signal gets passed through or not. The higher the weight for a particular input, the more impact that feature has, and vice versa. Each perceptron also has a bias, which can be thought of as how flexible the perceptron is. It is somehow similar to the constant b of a linear function y equals ax plus b. It allows us to move the line up and down to fit the prediction of the data better. Without b, the line will always go through the origin 0, 0, and you may get a poorer fit. 3. So these weights are summed over here with the inputs. Easy so far, right? 4. And then the sum passes through an activation function, which you can think of as a gate which opens and closes, or rather gives ones or zeros. That is if we are working with a threshold activation function. It also gives probabilities using either a sigmoid or rectified linear function. We'll discuss more on various activation functions in a bit. 5. So the output of our activation function is our output prediction, also known as y hat. Y is our actual observation and y hat is the value that the network predicted. These outputs can be continuous or regression values, binary values, or even categorical values. So this confirmation can be shrunk to a simpler representation known as a single layer perceptron. All what we discussed earlier happens in this one node. Layers of a neural network. A basic artificial neural network consists of 3 types of layers: input layers, hidden layers, and output layers. The input layer can be your features such as age, height, weight, hours of sleep, or even pixels in an image. Your output can be the value that you want to predict, such as whether or not it will rain, or even if a skin aberration is malignant or benign. Hidden layers of a neural network is literally just adding more neurons in between the input and output layers. There is a lot of power in the hidden layers of an artificial neural network. So data in the input layer is labeled as X, with subscripts 1, 2, 3 all the way down to M. Neurons in the hidden layer are labeled as H, with subscripts 1 all the way down to N. Note for the hidden layer it's N and not M, since the number of hidden layer neurons might differ from the number in the input layer. As you can see from the graph over here, the hidden neurons are also labeled with subscripts 1. This is so when you have several hidden layers, you can identify which hidden layer it is. Hidden layers with subscript 1, second layer has subscript 2, and so on. The output is labeled as Y with a hat, which is our predicted output. A neural network with more than one hidden layer is also referred to as deep learning or a deep neural network. Activation function. So before we move on to how neural networks learn, let's take a brief look at the activation functions. So there are various activation functions you can use, but we'll peek at the popular ones used for artificial neural networks. So looking at the threshold or step function we saw earlier, if the value of the sum weights and inputs is below the threshold, it is 0, and if it's above, it's 1. Think of our gate analogy. Simple. Next we have our sigmoid function, which is the most widely used activation function and looks like a step function but smoother. Here is our sigmoid function equation. This activation function is best to predict the probabilities. The output of the activation function is always going to be in the range of 0 to 1. So what is the probability that the picture is a dog or a cat? Hyperbolic tangent. This looks like a stretched out version of the sigmoid function, but it goes from -1 to 1. Reason you want to use this over a sigmoid function is because the gradient is steeper, hence the derivatives are steeper as well. Hence, deciding between the sigmoid or hyperbolic tangent function will depend on your requirement of the gradient strength. Rectifier linear unit, or ReLU, is very important for reinforcement learning applications. It is basically what it says, a linear function that has been rectified. So it is 0 in the negative domain and increments linearly. It gives an output x if x is positive and 0 otherwise. ReLU is less computationally expensive than 10H and sigmoid functions because it involves simpler mathematical operations. That is a good point to consider when we are designing deep neural networks. When you know the function you're trying to approximate has certain characteristics, you can choose an activation function which will approximate the function faster, leading to a faster training process. For example, a sigmoid function works well for classification because approximating a classifier function as a combination of sigmoid is easier than maybe a ReLU for example. This will lead to faster training process and convergence. You can use your own custom functions too. If you don't know the nature of the function you are trying to learn, then maybe it would be better to start with ReLU and then work backwards. ReLU works most of the time as a general approximator, but again, you will need to experiment with this. So how does a neural network work? Let's take a look at an example to get an idea of how neural networks work in action. So say we already train a neural network, meaning our weights are optimized for this application. We have our input layer, which is a set of features such as age, gender, distance to the hospital, income, and GP visits. Our output, which is our dependent variable of the probability that the person will be hospitalized. So intuitively, let's start with age. The older the person, the more likely they will be hospitalized, right? In terms of gender, men are statistically more likely to be ill enough to be hospitalized than women. We can use our data that we collect to find the correlation between distance to the hospital and being hospitalized. Same for income and visits to the GP. So what our neural network will do is that prior to training is to find patterns in the data and figure out how are all these figures related and connected. Once trained, you can enter your test variables, say age is 65, gender is female, moderate distance to the hospital, high income, and high GP visits. The neural network will work its magic and spit out the probability that the person will be hospitalized or not. We'll go into more applications of artificial neural networks in a bit. So now we have a holistic view of how a trained neural network operates. In essence, a neural network checks the combinations of different features and evaluates the various input features to find patterns in the data using a neural network architecture. Some may see this as a black box, but if you look closely, you may see some patterns emerge amongst the weights, inputs and hidden layers. The learning process. The learning process is easy to understand. In supervised learning, you have a relatively large dataset and then you feed in the inputs into the neural network. The weights can be randomized or predefined, depending on the application and outcome you require. The calculations occur through multiple neurons from the hidden layers of the neural network until it yields the output y hat. This is known as forward propagation. Next, we compare the result y hat with the actual output y. The task is to make the output value of the neural network as close to the actual desired output and reduce the error. If you are teaching a child math, for example, say the answer is 10, they calculated 6, you give the error of 4 and then the child performs calculations again until the error is minimized. Back propagation. We try to minimize the weights of the neurons for those that are contributing more to the error, and this happens while traveling back to the neurons of the neural network and finding where the error lies. This learning process is called backpropagation. Because we mainly have control of the weights, we can use backpropagation to minimize the predicted error of a neural network, and then we adjust all the weights simultaneously. We call it that because we propagate from the output to the input and adjusting the weights to minimize our error. So basically, how far are we from the correct output? We go back and adjust the weights slowly so that we get a smaller error in the next forward propagation iteration. We repeat this process for all the inputs and outputs in the training dataset until the error that we get is very small, for which is sufficient for our application. Now, how do we perform backpropagation? Now over here we have our simplified cost function, where we find the squared error between the predicted output y hat and the actual output y. We can first plot our squared error function j versus our predicted output y hat. At first thought, you can use the brute force method and try all the variations of the weights within the network, and you would get something that looks like a parabola of data points. Easy, right? Wrong. Though it may seem very easy, it would require a humongous amount of computing power. Think the fastest supercomputer on this planet. Now it would take that computer over 100 years to calculate the optimal weights for a relatively small neural network. We need to be smart about this. Enter gradient descent. Essentially, we can picture gradient descent optimization as a hiker. Let's call him Bear Grylls, the weight coefficient, who wants to climb down the mountain of the cost function into the valley, which is our cost minimum, and each step is determined by the steepness of the slope, the gradient, and the step distance of Bear Grylls, which is our learning rate. Considering a cost function with only a single weight coefficient, we can illustrate this concept like this. Of course, gradient descent needs to know which direction is downhill in order to work. Using our hiker analogy, Bear Grylls is sitting on the cost function canyon, knowing that he can find water at the lowest valley, the cost function minima, only knows which way to go because the part of the function he is standing on is sloped. Remember, he may not be able to see very far, and certainly not far enough to see where the minimum actually is. Bear Grylls' best bet is to go in the direction that is sloping downhill the most. You can see gradient descent in action with regards to linear regression. By taking baby steps downhill on a slope, we are able to find the line that best fits the data. Now Bear Grylls can take a lot of steps before evaluating where he is, or he can take baby steps and check his position. So we can have a big learning rate or a small learning rate. If we take 2 big steps in the valley before evaluating our position, we may end up never reaching the minima of this cost function. If we take baby steps, there's a good chance that we will reach our minima, but it would be a bit laborious and very long until that happens. So we can adjust our learning rate empirically till we hit the sweet spot, or we can use a learning rate decay, which you can think of as an adaptive learning rate. So the steeper your gradient, the higher your learning rate, and the smaller your gradient, the smaller the steps it takes to reach the final value. Stochastic gradient descent. Let's talk briefly about stochastic gradient descent. We'll go into details in another video, but essentially, while gradient descent or batch gradient descent computes the gradient of the whole dataset, stochastic gradient descent computes the gradient using a single sample from our dataset. On large datasets, stochastic gradient descent can converge faster than batch training because it performs updates much more frequently. We can get away with this because data often contains redundant information. so the gradient can be reasonably approximated without using the full dataset. Types of learning in neural networks. We have supervised learning, where the training data is input to the network and the desired output is known. Weights are adjusted until the output yields desired value. Unsupervised learning. The input data is used to train the network whose output is known. The network classifies the input data and adjusts the weights by feature extraction in the input data. Reinforcement learning. This is when the output is unknown, but the network provides the feedback whether the input is right or wrong. It is a semi-supervised learning sort of. Offline learning. This is where the adjustment of the weight vectors and the threshold is done only after the training set is presented to the network. It is also known as batch learning. With online learning, the adjustment of the weights and threshold is done after presenting each training sample to the network. Learning datasets in artificial neural networks. We have three main sets: a training set, validation set, and a test set. So the training set is a set of examples which are used for learning so that we adjust the weights of a neural network. One epoch comprises of one full training cycle on the training set. We have our validation set, which is a set of examples used to tune the parameters of the network. For example, to choose the number of hidden units in a neural network. And then we have the test set, a set of examples used only to assess the performance or generalization of a fully specified network, or to apply successfully in predicting the output whose input is known. This is also to check that we do not overfit our data. Let's take a look at the applications of neural networks. Many of the things we do every day involves recognizing patterns and using them to make decisions. So neural networks can help us out in zillions of different ways. They can help us forecast the stock market or the weather, operate radar scanning systems that automatically identify enemy aircrafts or ships, and even help doctors to diagnose complex diseases on the basis of their symptoms. They might be neural networks ticking away inside your computer or your cell phone right this minute. If you use cell phone apps that recognize your handwriting or on a touchscreen, they might be doing a simple neural network to figure out which characters you are writing by looking out for distinct features in the marks you make with your fingers, and the order in which you make them. Some kinds of voice recognition software also use neural networks. And so do some of the email programs that automatically differentiate between genuine emails and spam. Neural networks have even proved effective in translating text from one language to another. Google's automatic translation, for example, has made increasingly use of this technology over the last few years, and this is to convert one language, the network's input, into an equivalent word in another language, the network's output. There are many other applications which are way too much to discuss right now, but I'll just list them here for you to catch a glimpse. Okay, so that is it from me. Please don't forget to like, subscribe and share if you'd like to see more machine learning tutorials, and also please don't forget to support us on Patreon, link in the description. If you'd like to download the script in the video, please click the link down below and download for free. Stay tuned to the next lecture and we'll see how we can implement artificial neural networks in Python. Thank you for watching and see you in the next lecture.